Okay, so I messed up and stopped the recording, and we were just talking about how we deal with treating the data. So there's a couple important things. We can think about it pretty straightforwardly. This equation that we had written down, we can relate it to a line. So we make a plot the plot we want to make so we can figure out the delta H and the delta S is essentially natural log of the equilibrium constant on the y values, and then 1 over temperature for the x values. So ultimately, all we really need is our equilibrium temperature. Remember, we have careful experimental control to make sure that we are seeing those first crystals show up at a particular temperature where the concentrations we set up are the equilibrium concentrations at that particular temperature. They're not equilibrium at room temperature because we've got a bunch of solids floating sitting at the bottom. But when we heat it up, we can get to where that is the equilibrium temperature. So we had to have that really careful observation of the crystals forming. Ultimately, our x values are just the equilibrium temperature plus 273 inverse, and this is that. And then this is the part that we were just asking about that made me be like, oh, I definitely should record this, is how do we get our KSP value? Why is it just the grams molecular weight volume total squared natural log? Right, and we can talk about that as we look at how we set up our Excel file and kind of why we set it up this way. So potassium nitrate and the pre-lab example of calcium sulfate are both 1-to-1 ratios. So the 0.12 moles of potassium nitrate we put into solution becomes 0.12 moles of potassium ions and 0.12 moles of nitrate ions in solution. And so this becomes the K plus concentration is 0.12 divided by volume total. The nitrate is 0.12 divided by total volume. So it's 0.12 times 0.12 divided by volume total divided by volume. So it just becomes 0.12 squared volume total squared. It just becomes K plus squared. So we can just say our KSP value for this case is just the K concentration squared because we have this nice mathematical relationship for that. So in this setup, the 12 grams is constant. We started with that. The molecular weight of 101 is constant. The only variable is the volume total. Once we have that K plus, because of our setup, K plus squared is our KSP. Natural log of that is the natural log of KSP. So we just have to change this volume total value, and then the rest of this we can just click and drag, and it does all the calculations for us. Same thing with temperature. It doesn't ask you to do a temperature in Celsius, but I like having my data visible. So I can just put in my temperatures, then I do a Kelvin column, that's my Celsius temperature plus 273, and my inverse, which is my Kelvin temperatures inversed. This column becomes my y values, this column becomes my x values. These ones in circles are the only ones I have to input, the rest is click and drag. Now the question was, what if it wasn't something this nice? What if it wasn't a 1-to-1 ratio? So we're going to do some problems like that today in class, or not today in class, tomorrow in class. But let's look at what's going to happen. Let's do magnesium chloride. So if magnesium chloride falls apart in solution, this is our solid. I should also always be writing double arrows now because we know it's in equilibrium. So my magnesium chloride is going to go to magnesium 2 plus 2 Cl minus. That means if I started with 0.12 moles of magnesium chloride solid, that would get me 0.12 moles of magnesium, but it'd get me twice as much chlorine. So that would get me 0.24 moles of chloride ions. So we end up with twice as much chlorine. The other thing that's a big change is my equilibrium constant is now going to be magnesium ions times chloride ions squared, again at equilibrium. So I'm going to have 0.12 times 0.24 squared in that situation if it wasn't a nice 1-to-1 mole ratio. It's not actually much more difficult, but there are some extra thought steps that are really important we don't forget if we're dealing with something that's not a 1-to-1 mole ratio. Other questions?
Did you put the square because 24 is double?
No. So there are two places where that coefficient of 2 comes in, right? There's the stoichiometry, which is why it's doubled. It's the stoichiometry. It's a 1 to 2 mole ratio. But then there's also the energetic argument, right? The delta G. So our definition of the equilibrium constant, this is like the definition, right? It is the concentration to the power of the coefficient, concentration to the power of the coefficient. So magnesium, concentration to the power of 1, chloride, concentration to the power of 2.
Okay, so like when I get like this number in front of the element, you just match it when you put it
For the powers. Yep.
Okay.
So that, it is weird. Are you taking Chem129 in the future? So that's a really important detail in Chem129 that a lot of people didn't catch in 128. The fact that that coefficient has two things it does. It affects the stoichiometry, and it also affects the thermodynamics. And so it affects that stoichiometry in terms of the number of moles we have, but it affects that thermodynamics in terms of how many multiplications of the concentration we need. And so it does do two different things, that coefficient does. Other questions? Yeah.
For the volume total, you convert that to liters, right?
Oh, yeah, definitely convert it to liters. Yeah, convert it to liters. So 0.014 liters, yeah. Other questions? Let's do that now. Fix that real quick. 0.014 liters. Other questions? Yeah.
Might be dumb, but what is the concentration of the potassium?
Wait,
Like,
so the concentration of the potassium depends on what we did in the experiment, right? We chose, how many grams of potassium nitrate did you put in? Should be about 12. The procedure said to do 12. And then how much water did you put on top of it? 9 milliliters, right? So we made the solution. That's where we get the 12 grams. And now, when we add the 9 milliliters of water, it's not how much water you put in, it's the total volume. And that much, 12 grams of potassium nitrate takes up some volume. So when we make our solution, the total volume of the solution ended up being 14 milliliters.
So is it okay if we just keep the 14, or do we have to do it, like, do we have to convert it to liters? Because on here it says, it just says milliliters.
You can list it as milliliters, but when you do this division over here, it has to be in
liters.
Yeah.
Okay.
So we could, here's the other thing we could do. We could do, if we have our volume total in 14 milliliters, we'd have to have volume total divided by 1,000 over here, and that starts to look pretty funky.
Okay, gotcha.
But either way, is when we do this division, we need it in moles per liter.
Good to know. Okay.
Okay. I'm gonna stop recording this, and I'm gonna come around and help each of you with your like whatever graphing issues you're having. Does that sound good?